Good morning, and let's start the last and final lecture regarding multiple linear regression. And this week we started with extension to multiple linear regressions. Okay? In the beginning of yesterday's lecture, we said we will relax some of these assumptions and we will see applicability when we reduce those assumptions. Right? Remember you? Okay, it's working. So, today what we are doing to relax another assumption, which is heteroskedasticity. Okay? And what was that? From yesterday, if you remember, okay? We derived all these errors. We said the error of the residual is what? They are dependent on each other. Then we need a way to make them independent. Okay? So we had to make two equations, solve equation number 1, which is this for the residual term, solve equation number 2 for the residual term, then take the ratio between them. Okay? And this way we prove what? The null hypothesis. Okay? Now then we said heteroskedasticity as a function of the explanatory variable. Okay, so we say that our explanatory variable could affect the variance of the disturbance term. Okay, if this is the case, then we have to perform a test. And in this test, what we do, first of all, to organize all of our disturbance term in increasing order. Okay, because the disturbance terms are randomly distributed. So what we do is to take them, and we are dealing with the time series data, so we rearrange them. Okay, then we split them in between the time series. So we split in two halves. We estimate the regression coefficients for the first half. For the second half, we compute the ratio of the sum of the residuals. Okay, and that gives us the appropriate F distribution. Now, the same idea we can modify it. Okay, so the splitting of the time series we can modify it. What we can do here is to exclude the middle part of the time series. Okay, so if we have a time series like this, okay, we have T1, T2, okay, and Tm. So what we do, we take this part, the middle part, we exclude this from our series, okay, and we just take this part and this part, the final part of our series and the beginning part of our series. Why we do this? If there is a difference in the variability of the disturbance term, so as we evolve, this variability may increase. Okay, so then the assumption like we had made, the variance is constant, does not hold anymore, and we fan out those residuals. Okay, something like this. Okay, so this is an example where we have the income and expenditure of a data set, where we took the first 150 individuals, the residuals of the first 150 individuals, and the residuals of the last 150 individuals, and we plot it. Okay, so we see in the beginning the residuals are almost behaving well. They are in the constant row. But as the time series evolve, we see those residuals now fan out. Okay? So they are no more constant. Yes?
Professor, from the time series data, we are taking the start part and the end part, and we skip the middle part.
Yes.
And the graph in the scatter plot that is showing in the last, the data is scattering or going to different sides. So is it predicting the middle data or what they are doing? I don't get why we remove the middle part and what we get from this. I don't understand.
Okay. So this is not real data. This is, we are talking about residuals, the error term in our data. Okay? So usually when we are building our linear regression or multiple linear regression, we make this assumption, and the assumption goes as follow. We say any random errors coming into our model, we assume those are constant. Okay? So if those are constant, they around the fitted line of our regression, they does not behave randomly. Okay, they are constant.
So if they are scattered, meaning there's a margin of error or what we say, it's far away from the fitted line.
If they are scattered, this means the assumption we made about the variance is constant does not hold anymore. Okay? So in this case, we saw here is heteroscedasticity. So we reject the hypothesis, the null hypothesis where we were saying that homoscedasticity is true, but in reality we saw is not the case. Okay? And in MATLAB, you can do it this way. Okay? We read our table. First step is to sort all the rows in increasing fashion. So we use the function sort rows. Okay? Then we count the number of rows of this newly sorted data, which is n. Then we fit our regression model. Okay? So the sorted data, we want to do what? A linear multiple regression, and this is for the first half of the data. So we exclude, yeah. Similarly for the second half of the data. And once we have these two results, we just from the first model, we get the sum of square of errors. Similarly from the second, we take ratio of this, and based on that, we calculate p-value. If p-value is less than what? Yes, but the general rule is we kind of memorized this rule yesterday. If p-value is less than 10 raised to the power minus 2, we say is highly significant. Okay? If this value is greater than 10 raised to the power minus 2, then it's not the case. Okay, now we also made another assumption, and we say the correlation between two consecutive error terms is equal to 0. There is no relation that does not depend on each other. But often in reality, also this assumption is violated. Okay? Similar to the variance. So in real data set, usually also we see this covariance is not equal to 0. Okay? For example, if you have a time series data and you have a stock time series for a stock market for stock prices, usually the future majority of the time depends on today, the previous day, or past week, or last year. So there is some kind of momentum, okay, and that momentum also come into the picture of the error term. Okay, and you can have many more examples. So the key idea behind this is the identity of the autocorrelation test. Okay, and this says if you have two consecutive disturbance terms, disturbance term at t, the second one at t plus 1. Okay, if we use the identity to take expectation and take the difference between the two consecutive disturbance terms, so a minus b whole square, a square, the first term square, the second term square, minus twice first second. Okay, so this is actually what, from here we can get the idea if there is the relation, because they are the cross terms, they are close terms, consecutive terms. Okay, if the disturbance terms are uncorrelated, so this term should be equal to 0. Okay, if there is a correlation, this term will have a positive value. Okay, and this is the idea. On this idea we will build the Durbin-Watson test. Okay, and this test will give us the idea if the disturbance terms are correlated in a given data set or not. Okay, now moving ahead, looking to what this Durbin-Watson test is. So this was our identity, we saw it before. We say if this term is equal to 0, the disturbance terms are uncorrelated. If they are positive, this means that sigma and sigma, so they are 2 times sigma square. Okay, if this is 0, so it has the usual sigma, they're 2 times 2 sigma square. Okay, this means the two error terms are far away from each other by 2 times sigma square, 2 times the variance. Okay, but if this term is greater than 0, then what we have, the difference between the two disturbance term will be less than 2 sigma square. This means that now these two disturbance terms are close to each other. If they are close to each other, it turns out that they have correlation. Okay, and the formal test for the Durbin-Watson test is this formula. Okay, this is what we saw before, the difference between two consecutive error terms square. So kind of we are doing least square for the two consecutive disturbance term, and we subtract them, divided by the error square. If this value is approximately equal to 2, we say those errors are uncorrelated. If this is less than 2, we say the correlation is positive. If this is greater than 2, we say we have a negative correlated disturbance term. Okay, now if we apply and see the connection of this test with the first order autocorrelation. So the first order autocorrelation is something like this. Okay, the relation, we multiply two consecutive error terms divided by their squares. Okay, so this gives us the first order autocorrelation, and if we include this into the Durbin-Watson test, it can be rewritten in this shape. Okay, we don't need to go into too much detail, but just to have a general idea. Okay, this term, if we have a long series, if we have a long time series, this term is approximately negligible. Okay, so the ratio of these two is negligible, so we ignore this term and then we left just with this. Okay, which is d approximately equal to 2 times 1 minus R1, and R1 is the first order autocorrelation between the two disturbance terms. Okay, and then the rule is if R1 is greater than 0, if this value is greater than 0, this means that this term 1 minus something greater than 0, we will have what? A lesser value. Yeah. So this means D is less than 2, and the other way around if this is greater than 0. Okay? Same thing here. Now, okay, this. Okay, to do the Durbin test, what we do in MATLAB, for this test we get two values, the p-value and the Durbin-Watson value, and we should get the idea if this value is greater than 2, less than 2, or equal to 2. Based on this, we make the conclusion if the disturbance terms are correlated or they are not correlated. The idea is clear. We're following? Okay. So, first you define the residuals, okay? If you have fitted a model, for example, we fitted a model, we call it MDL2. From that model, we pick just the residuals, okay? Because we are dealing with residuals. And we take all the residuals from our fitted model, okay? And then for the test, we use this function in MATLAB, which is dw test. And it takes these arguments. The first argument is the residuals from our model, okay? Then all the values of ones. Remember, in our design matrix we had the intercept is all equal to ones. 1, 1, 1 for each row. And we exclude the last explanatory variable from our data. Remember, if we are including the intercept, so we should remove one of the variable. This is the same thing here, okay? And the test is a tail test. In this case, we do the right tail, so we should mention it's a right tail, okay? Is it clear? So this is how we implement the formulas in MATLAB. If we run this, we get these values. The Durbin-Watson statistics is this, and the p-value is this, okay? So this value is less than 2. If this value is less than 2, this suggests that there is a positive autocorrelation between the disturbance terms, okay? And the p-value, we see it's on the borderline, 10 raised to the power minus 2, it's very close. So we say yes, there is a mild autocorrelation looking into this data. Okay, we started from where? Okay. Now, when we started studying time series, we had one dependent variable, which is the output of our model. And then we can have several explanatory variables. Okay? Now, how should we select those variables to get a good model? For example, if we have a dependent variable, we have one dependent variable and we have 28, let's say, explanatory variables. So we can include all of these. So we will have 29 betas, 29 coefficients. So we are making the model very much complex. Okay?
You can see correlations between the variables.
Yeah, that's what we will do next. If we have more variables, the interpretability of the models becomes difficult because each coefficient needs its own explanation then. Okay? The model becomes more complex.
We can do it on like in a PCA, like we take the variables that
Yes, that's what next we will do. To which variable keep and which to throw away. Okay, but the general idea is if you have more variables, sometimes there is a fear that you are overfitting your model. Overfitting means you have more explanatory variables and some of those explanatory variables does not help your model. They're kind of burdening your model. If when they're burdening, this means that then you have the variance is not constant. You are then moving to the case of where we have perfect collinearity. We saw yesterday. When we have that perfect collinearity, then the rank matrix is not a fully ranked matrix, and then we cannot take the inverse of that matrix. So the result is then the confidence interval is so long. Okay, are you getting my point? Okay, so the goal here is to build a parsimonious model. Parsimonious means that you take less explanatory variables, you just choose and pick those explanatory variables that explains your model in a good way, and you reduce complexity. Okay, is the rule like Occam razors, so the less the better. Okay,
is it like the same concept as dimensional reduction?
yes,
Like you simplify
you simplify, and the more you simplify, the better is.
with the less reduction of like you lose as little as possible while trying to lose as little as possible.
Yeah, sometimes, okay, there is also a trade-off if we go really in detail, but on the upper level, you should look for the more you can simplify, the better. Okay. Okay, here we are. Oh, okay. So the goal is to build a model where we include those explanatory variables that explains our model best. Okay, and we remove those explanatory variables that those are not significant for us. Is it clear the idea what we are doing next? Good. Okay, so we can do it in two ways. The first one is to go forward selection. Okay, by forward selection what we do is to start with no regression. Okay, we have just the error terms and we have the intercept in our model. Okay, then we slowly add variables and each time when we add variable, we fit the model, we look to various values, for like value of f, the p value, and based on that we decide if the new variable we added, how is its p value? Is it significant? Is it insignificant? If the new variable we added has high significability, we keep that variable. If is not significant, the p-value is greater than 10 raised to the power minus 2, we remove that explanatory variable. So we keep on going this. Okay, we add variable, we refit the model, we check the r square value, the f value, the p value. Okay, and we stop when no other variable is significant for us. And the other way is to go backward elimination. In the backward elimination, we include all the explanatory variables plus the intercept. We fit the model the first time when we have all the explanatory variables and intercept. We fit the model. When we fit the model, what we would get? If you remember from yesterday. When we fit a multiple regression model, we get the estimated value of the coefficients for each model. Okay, so if we have beta 1, beta 2, okay, let's say x1, x2, x3, and we can go on. So for each beta, we will have its estimated value. Okay? For this one, for this one, for this one. We build that table. Okay? So for beta 1, beta 2, beta 3, we have something like this. If you remember from yesterday, here we have the p-value. Okay? And here we have the estimated value of this column. So we check if the p-value for beta 1 is highly significant, we keep this explanatory variable x1. Okay? If, for example, for beta 3, the p-value is greater than 10 raised to the power minus 2, we exclude this and we exclude this. Okay? Is it clear? Okay. And we stop when all the variables are significant. Okay? So we remove the unsignificant variable, we just keep the significant variables. Okay? And yes?
Do the two selection models create different results, or do they get the same result? The same model?
No, they get to the same results. They get to
So
the
it's
same
not,
results.
it's in it that you can choose.
Yes, depends on how you like it. But it's very easy in MATLAB. You just here in the code, in the criterion, you say you want to do it forward or backward. Okay? You fit your model, your explanatory variables, the dependent variable, and you see this. Okay? And this process of backward and forward is called stepwise regression. Is it clear? So the decision to include a variable or to remove an explanatory variable is based on the value of f and the value of p. Okay? Based on those two values, we make our decision to include an explanatory variable or to remove it. Okay? Now, let's see this in action in an example. Okay? So we have a marketing study, and the data set has 80 consecutive weeks. Okay? They have data for 80 consecutive weeks. The response variable, the dependent variable, is log of the units sold. Okay? So they basically want to see, they have a product A, they want to sell this product, they want to see which variable is really affecting the selling of this product. Okay? So we have 9 variables to sell this product. For example, the first variable say the number of receipts with product 1. Okay? Is there some promotions or not? Is there some time trend or not? How many items of this product is sold? Okay? So there are various explanatory variables to know how many products we sold. Okay? Are you with me? Okay. So the goal is to identify which variables are significant and which are not. Okay? Good. Okay. So step 1, for example, we want to use backward elimination procedure. In the backward, we fit full model, okay, with all the variables. So we take all the 9 variables, the 9 explanatory variables in this model. Okay? So we have the intercept, beta naught, and then 9 variables, beta 1 up to beta 9. Okay? And we compute the t statistics and the p value for all of this. Based on those, we see the variable 8, 4, 2, 5, these are having low significance, okay? So we remove them. Are you getting my point? You're looking confused. So we have 9 variables, explanatory variables. We want to know which variables are significant for our dependent variable y, okay, for the product A. We run the stepwise regression. In the stepwise regression, each time it removes those explanatory variables which are not significant. So if you run it, yes, with the p-value. So if we run the backward elimination procedure, we remove variable x8, x4, x2, x5, okay? So those are not significant.
Only in one iteration.
No. You fit the model once, you compute the p-value and all the statistics. Then you see, okay, x8 is not significant. We remove this, then we refit the model. Okay? Then again we look to the statistics. So in this case, x4 is not significant. We remove it, we refit the model again. Okay? So when we remove those, our model becomes like this. Okay? This is the intercept. Yes? Yes. Yes. But we should also be very careful about R square. Sometimes R square value is really good. This means that, yes. But sometimes if you test it with a value from outside, to do prediction, it performs really poor. Okay, so there is this trade-off.
For example, right now we have only 4 to 5, 9 variables. And there might be a case where we have 50, 60 variables.
Yeah.
So don't you think it's a lengthy process to eliminate insignificant variables? Because we need to start from first, because we want to eliminate, so we eliminate one, then we test the model in each iteration. So don't you think it's a lengthy process?
For MATLAB, it's easy. For us, it's lengthy. But even before this, whenever you are doing data analysis or in the field of data science, everyone can fit the model. Okay. Fitting the model is just one line. Okay. The crucial part is the data engineering. Okay. Which variable to choose, which not to choose. So even before putting your variables to the model, you do some data analysis on your data. So majority of the variables you get rid from them there.
And one more thing, sir, in the backward selection and forward selection, is there any significance where we can decide where to use forward selection, where to use backward selection? Is it any significance or?
No, it's your choice. It's your choice, as you feel comfortable. Okay, so when we remove those models, now our model becomes like this. Okay, these variables are left: x1, x3, x6, x7, x9. Okay, and we calculate the final R square values are 0.67 and the adjusted R value is 0.65. Okay, so overall the model has explained the variability when we just keep these explanatory variables. Okay, so we kind of build a parsimonious model. We used less explanatory variable and our model fits well, and it's explained the majority of the variability. Okay, and in MATLAB we use this function. Okay, so we read the data. This is the usual process we all know by now. Okay, We keep all of our variables, the dependent and the independent. Okay? In the question, it was said that the output variable is a log transform. Okay? So we take the last column, which is the dependent variable, and we apply log to that column. Okay? This was the question, I'm not saying. This was in the exercise. Okay? And when we apply the stepwise, we use this function, stepwise lm. Our input data, we wanted to use linear model, linear regression. Upper here means, when you put upper, this means that we can only, the complex model we can use is what? Linear. So this is important to mention. To use just linear model, otherwise it can take to another model. Okay? And when we do this, we get those values. Okay? So, let me show you here if we can. No. Okay, let him work. Now, some exercises to really get the idea, okay? Let's say we have a data set and we have the daily consumption of methane gas. Okay? The data set is from the company Cons Gas. So, we have a daily consumption for the methane gas. We have those observations in our data. Then we have another column which is the mean temperature per day. Okay? And this is for the whole month of February. So what we have? Three things. The daily methane gas consumption, the temperature, and daily data. So what the exercise is asking is to look for some trend, weekly seasonality, okay, and the temperature effect.
Observation of what? Daily observation of what?
The methane gas, the gas consumption.
So that's what we do.
Yes. Per day, one reading for methane gas. Next day, another reading. Third day, another reading. And for the same day, we also have temperature. So first day, for example, it's winter, it's cold, temperature is down, we will have high consumption of, because we are cooking biryani. Okay? Okay, so the first question is to estimate the regression model. Are you with me? Give me feedback. Are you with me?
Yeah.
Good. So the first question is to build the regression model. What we have in the regression model now? The intercept, the trend, the seasonality, and the temperature. So this is our full model. Okay? If you remember from the exercise of yesterday, we said if we want to include the intercept, brilliant. We have to remove one dummy variable. In this exercise, the question is asking to exclude Wednesday. Okay? The question is clear. We want to build the regression model and remove this. Okay. So two things. We have trend, seasonality. So for us, trend is like an arithmetic number. It takes values from 1, 2, 3, 1. just to have a check if the general time series is increasing or it is decreasing, okay? And seasonality in this exercise for us is weekly. So, okay, each week has 7 days. It's clear? So we could build two types of model. Either keep all the dummy variables and remove the intercept. Either keep the intercept and remove one dummy variable. And the exercise is asking to do this. To keep the intercept, remove the, and which is day Wednesday. How we do this? Okay, let me find it now. Okay, looking here to the code, we read our table. Okay, the important thing here is this line, the row time. In the data set we don't have, and it's a time series, so whenever we want to insert the date time, we use this function, date time. Okay, and they said to us the data is from February, so we say the date time starting from 1st February 2024 to date time 28 February 2028. Okay, so this way we create a column of time of dates. You with me? Okay. And similarly we need for seasonality the weekdays. Okay, so how many days we have in a week? Okay, so the function we can use is weekday. Okay, and we apply this weekday to our dates. Okay, it is important distinction now. Pay attention here. Usually in MATLAB, it start the values of the week from Sunday. So to Sunday it's a 1, Monday 2, Tuesday 3, and so on. Okay? And we also know that in this kind of models, it takes the first value when we are, let me rephrase it. When we are building this kind of model, where we remove one dummy variable, the regression model considers the first entry as a reference categorical or dummy variable. Okay? So in the exercise we have Wednesday, and Wednesday should be number 3 or 4. 4. So we say from 4 to 7. So Wednesday, Thursday, Friday, and then we again start from 1, 2, 3. Okay? So this way we assign the categorical values to. Okay?
But we have the ordinal true. We have the ordinal.
This or this?
Categorical, and then not ordinal true. To say follow that.
Sorry.
We are in the categorical. We also can include the ordinal true or false.
Okay, in this case no. Why? Because yes, in this case no, because we are defining this. We are defining this. If we are not defining this, then okay. And then the next thing is to include the column of the trend. Okay, so trend for us are arithmetic numbers from 1 to n. So y, we append to the data set, y, we append what? The new column called trend. So trend, this, and then we append these days of weeks to our data set. Okay, are we good? Then we fit the model. Okay, so what's our model? We have the intercept, we have the temperature, we have the trend, and we have day of the weeks. Okay, so those for us are dummy variables, remember? Okay, and when we do run this, now see, our model was what? The intercept, temperature, trend, day of week. So day of week is seasonality, this is trend, meaning we have a time series. Okay, and now look here, as I was mentioning before, if you see closely here, these are the estimates of the beta. Okay, the estimates of these betas, beta naught, beta 1, beta 2, So looking into all of these, if you see, the intercept is significant, all the rest are significant, but if we see Tuesday is not significant, okay, we can notice this from the model, at least by now. R square is 0.95, this means majority of the variability has been explained, and the p-value is -11, so we are doing good. Now, what's the next question is, okay, you can also interpret these values. If you remember from yesterday, we said that here everything should be with reference to what? With reference to the dummy variable which we removed. So in this case we have Wednesday. So for example, if you want to see this, the trend or the, okay, look here to the trend. Its p-value is 0.07, which is not significant. What this means? We have trend, okay? If the trend value is not significant, this means this p-value is greater than 10 to the power -2. This means it's not significant. If it's not significant, we need to remove the trend. This means we don't have a trend in this data set. Are you following me? Let me repeat. Our model, what was our model? We had the intercept, we have the temperature, we have the trend. Intercept, temperature, trend, we have for seasonality, days of the week. Am I correct at this point? Okay. What we have to check? We have to check for trend and seasonality. We fit the model. Okay? Now looking into the trend here, its p-value is greater than 10 to, which is 0.07, okay? So greater than 10 to the power -2. So if it's greater, this means it's not significant. We should remove this trend. This meaning our time series has no trend. A general trend is absent. Okay? Similarly for the other betas, for example, for the temperature, we have this. And its p-value was very, very low, so this is highly significant, okay? Trend value, which was 0.08, so not significant, okay? For example, the consumption on day Thursday. If we see the consumption on the day Thursday, where is it? Day Thursday, which has this value, this huge value, okay, for the coefficient, which means that this huge value, consumption on day Thursday is about this much unit higher than Wednesday, okay, because everything here is with respect to the reference, the dummy variable which we removed, okay. Similarly for the others, okay. This consumption is greater by this amount with respect to Wednesday. This is greater by this amount with respect to Wednesday. So for everyone, okay. Similarly, you can make conclusion. Now, what we do, we remove the trend, okay. How we remove it in MATLAB? We say remove terms. This is the function, and from our fitted model we remove the trend, okay. Now our model becomes what? The intercept, the temperature, and day of week. Before it was like this. We had the trend. Now we remove the trend. Our model becomes like this. If we do again the recalculation, we get these values. So the R square value has increased, okay. Okay, we refit the model. Now we see, look to the values. We don't have the trend now. All the values are highly significant here, okay. And we have what? The overall p value is this. The R square value is this, okay. So what we did, we removed a variable which was not helping us, okay. If we had included that variable and many more variables like this, we would have overfitted our model, okay. So we have to get rid of this. And then if we fit the model, okay, by doing this, okay, let me do it from here, okay. Now the next question the exercise is asking is this. Where is it? Okay, we did these first two parts. We fit the model with reference to this. We remove the trend because the p-value was greater than this value. Now we want to see the seasonality, okay. If you remember, we did a kind of exercise yesterday. So the trend is missing, but now we want to make sure if there is seasonality. So for this we have to test the hypothesis, and we assume the null hypothesis, all the betas of the seasonality is equal to 0 for every day. If the beta for every day is equal to 0, this means we will have a flat line, we have no seasonality, okay. And remember, here also we have the Wednesday is the reference day, okay. And to check this, we do it by this. If you remember from yesterday, it's the F test we perform, okay. We do the F test to see if there is seasonality or not. And this is this term divided by Q. Q is the total number of coefficients, okay. The number of restrictions you are putting into your model. So in this case we have 6. okay, the intercept, and 6 days. This was for the reduced model. Reduced model divided by the full model. Okay. So in the reduced model, what we have? We have the intercept and we don't have the Wednesday. So we just remain with 6 coefficients. In the full model, n is the total number of observation. Okay. So in this data, our observation is 28. Okay. And k is 8. Why? Because in the full model, here, in the full model we have 8 coefficients, 8 restrictions, let's say. Okay. We put these values and we got this. Okay. P-value is very, very less. So it's strongly we reject the null hypothesis. Okay. And this means what? We have seasonality. Okay. Are we good? Okay. In MATLAB, how do we do this? Okay, the same equation we have to replicate in MATLAB. Okay. So first of all, we remove the weak terms because we say they are equal to 0 for the null hypothesis. Okay. Then we simply apply the numerator here, which is this one. Okay. And then the denominator. So for the reduced model, we take the error term from the reduced model and from the full model, n minus k. K is what? The estimated coefficients. And then we take a ratio of these two. And based on that, we find what? The p-value. Okay. So the same thing here. Okay. This is the numerator, this is the denominator, and then we take the ratio. So this is the reduced model, this is the full model, the residuals of the reduced model, residuals of the full model. We take this its ratio, and from this ratio then we can calculate the p-value. Okay. So to calculate the p-value, we use this function FCDF, and this function accept these values. The ratio which you have calculated before between the reduced and the full model into n minus k. Okay. In just upper, in the case we want to use just the linear model. Okay. Are you with me? Similarly, we applied this thing manually, if you see, but it turns out that we can also use something automatic, okay, which is alternative way of doing the same thing to calculate the ratio and get the f value and the p value. How we can do this? Let me explain it from here. Yesterday, if you remember, we said we have to test a model, we can have different linear combinations. For example, for the general null hypothesis, we say beta equal to 0. We could have another possibility, beta 1 equal to beta 2. This could also be a null hypothesis. But in this case, we say the seasonality is absent. We want to see this. So this means if seasonality is missing, all the coefficients of the seasonality of the day, Monday, Tuesday, Wednesday till Sunday, beta 2, they will be equal to 0, all of them. Okay. And we said C times beta equal to C. you remember this from yesterday, we said C beta equal to C. Okay? And this was what? A row matrix, this was a column matrix, and we multiply these two. And based from this, then we get the matrix of C. And that matrix of C here is, we need zeros of 6 rows, 2 columns. Okay? So this means we have 6 rows, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes. What this means, no intercept. One of the terminals goes that way. Is the trend, yes. Is the trend, no trend. And then we will have the identity matrix. Okay? So, to do it automatically, what we did this way, we define this matrix, which is C equal to this, and based on this, then we can find P value and F test of the coefficient value. Okay? Okay? So, and we can plot this. Okay? So, is here, looking here. And then finally, we can also fit our model to do prediction. Okay? So one of the question was to, let's go back to the exercise where we are now. So we check this point, okay? We say the null hypothesis, we reject the null hypothesis. Why we reject the null hypothesis? Because the p-value has significant value and there is seasonality. Okay? Why? We rephrase it. We have seasonality because the null hypothesis, all the betas were equal to 0. We suppose this. But when we perform the test says something different. The p-value is much more less. So this means based on the value of p, we reject the null hypothesis and we say there is seasonality. Now it's clear. The next thing is to see the goodness of the fit line, okay? So to see how our model is good or not. And we take this decision based on the value of r square. So in this case, we have a good r square value, meaning the model is fitted well. Okay? Okay, we did this. Now to fit the model, okay? In MATLAB, we can do it this way. Y hat our model dot fitted, okay, and then we plot it. So we get something like this. Can you see here this figure? Yes? No? If you see, the blue line is the original consumption of the gas, and the red line is the predicted value. Closely looking to this value, okay. This should be, no, yes, this should be the first, this should be the first one. So, the predicted value follows the original consumption of methane gas very closely, okay. So the residuals are very small, and we can see here we have seasonality also. So there is no general trend, but seasonality is there. Okay. Now, okay, we did this. Okay. Now to do prediction, so we have the data from all of the month of February. Okay. We have the data for the month of February. Each day we have observation for the consumption of gas. Each day we have temperature. Now we want to predict a value which is outside from the month of February. Okay, and the exercise say to predict a value on Saturday 10th of March, and the mean temperature at that day is 15 degree. Okay, so we need to predict this. To predict what? The consumption of gas on Sunday 10 March, the mean temperature at that day is 15 degree. Clear? So our model becomes like this: y equal to the intercept, the estimated coefficients beta for Saturday, plus temperature of that day, multiply by the given temperature. So here we have the average temperature, but here we have the coefficient, and here the mean temperature is given to us by the question. Okay, so we get this. Putting all these values, we get something like this, which is this huge value is, is the consumption on that day. Is it clear? No, no one is following. What we are doing here? Of what? Yes. Okay, so you're still alive. Yes. Good. Okay, but to do this, here is a trick. Our model, we cannot feed to our model just values like this. 10 March, 15 degree, predict me the consumption. No. We have to give it to our model the same way our tables are arranged. Okay? So where is the column of the temperature? Where is day of the week? Okay? So we have to arrange it in this shape. So the new value, the value for which we want to make prediction, should have a shape like this. So it should go to down the temperature column, which is 15, and day of week should go to the column of day of week, which is 15, and then we do prediction like this. Okay, looking here how we have to arrange this. So x0 is the new value, the value we want to predict. How we arrange this, as I said before. Okay, let's say we want to put the new entry at row 3. You can put it in any of the entry. Okay, so let's say we put it in row number 3, the new entry. What is the new entry? 15 degree and 10 March. So row number 3, column number 2. Column 2 we have this value, temperature. Okay, in column number 4 in our data set we have days of week. So now is the correct shape our model accepts. Okay, is it clear at this point?
Like switching observation with a new one. Like we add the
Yes, you are making a new entry into your data, basically. And then you predict, okay? You predict with what? With your model, which is the model you fitted before, but now you are giving it a new value. okay, which is x norm, and you predict the new value, and we see the results. Where is it? Okay, so it takes shape like this. Okay. Now this one. Here. Okay. Now you can do the, okay. So the same question is asking to do what? The final step in this exercise is to, where is it? Okay. If you, to the final exercise, which is your homework, and then I move to the next exercise, okay? Which is to de-seasonalize your time series. Okay? So we have a time series. We know there was no trend, but there was seasonality. But now the question is asking to remove seasonality. And when you remove seasonality, you get something like this. Okay, before, when we had seasonality, it was capturing the sharp edges of our plot. But when you remove seasonality, okay, good. Now, okay. So in between the slides, you have solution. Okay, now, next exercise. I need your attention, please. Exercise is saying we have in the US, from the US market, we have annual time series of meat consumption. We have these explanatory variables: beef consumption, retail price unit of beef in US cents, per capita income, and the goal is to see the consumption of pork, okay, using the other explanatory variable. So the question is clear. We want to know pork consumption based on these x1, x2, x3 explanatory variables. The first question is to fit the model, okay? And the second is to eliminate the explanatory variables which are less than 5%. So our model becomes like this. We have the intercept, we have beef, we have price, we have income, okay, to know the pork consumption. Is it clear? Please, if it's not clear, tell me. Okay, so this is our model, okay. In MATLAB, simply we take our data, we fit the model, and we have the output, okay. So we have our data, we fit the model, and so here we are. So in the first case, here our model was the intercept, beef, price, income. We have something like this. Looking into all the coefficients, the p-value, all of the explanatory variables are significant, so we keep all of them. Okay? Looking here into the intercept, what do you think? The value of this intercept has some meaning for our model or not? Yes, it has no meaning for our model because we have involved price and everything. If we move everything, the price to the intercept, which is 0. So this case. Okay. So here we have price, right? And here we have consumption. What's the consumption of what? Of pork, of meat. So the intercept is 189. This means here. And here the price is 0. Okay? This has no meaning for us. If we take this into consideration, this would mean that at price 0, we have this much consumption. It doesn't make sense. Okay? Yes, for free. So no meaning here. Okay? The same results here. Okay? The overall model R square is what? So 84% of the variability has been explained by our model. Okay? And p-value is 10 to the power minus 6 for all the models, so it's highly significant. And similarly, you can explain all these variables, these values. So, who can answer this question? If we have 1 unit increase in price, if the income, for example, is increased by 1 unit, what will happen to consumption of beef here? It will reduce by this amount. Similarly for the others. So you can make these conclusions, okay, based on these estimated values. And the right way for the exam is to make comments like this. So what this means, if beta 3 is equal to 0.168, this is 0.168, beta 3, income is 0.168. What we say? Holding beef consumption and price fixed. If you keep the rest of the variables fixed, okay, and then a 1 unit increase in income, it corresponds to an average increase of this much consumption in pork. Okay, so the comments should be something like this, very clear. If we keep the rest of the variables fixed, and if income is increased by 1 unit, then the consumption of pork will increase by this amount. Is it clear? Clear. Similarly for the other explanatory variables, for the other coefficients, okay?
For example, if price is increasing, then consumption will reduce.
If price is increasing,
It's 1 by 1, let's say. Then consumption will be increase or reduce? I think reduce.
it's increased.
It's get expensive. For example,
Yes.
For example, if income is increased, so consumption will be increased.
Increase.
But my question is that, for example, if price is getting increased on a product,
That's related to price. You're correct. Before we were talking about income. Now you're saying price, okay? So with the price is a different story.
yes, that's what I'm saying.
So with the price, it decreased by this amount.
So if the price goes up by 1 and we keep the income fixed.
By beef by this amount will be decreased, and this by this amount.
The consumption decrease of minus 3. No.
Sorry.
Example, like in the price minus 3. If the price goes up by 1, the consumption of pork reduces by 3. And while keeping the beef and income fixed.
Constant. Yes. Good. Similarly, for the same which we did before, you can calculate the Durbin-Watson test. Okay? Durbin-Watson test was for what? Yes, if there is a correlation or not. Okay? And we do this in MATLAB like this. Maybe I have it here. Okay? Similarly, just we did before. Do you have any question? Okay. So, for the Durbin-Watson test, you can do it this way. You can calculate all those values from the reduced models, the residuals. Now, what was Durbin-Watson test? We have a sequence of data. Okay, we take the first half, we take the last half, we exclude the middle. Okay, we take the error term from the first half, divide by the error term from the second half. Okay, and we have this ratio in based on, so here, look here. Model 1, we exclude that part. Model 2, we exclude that part. Yeah. And then we have residuals from the first model, from the first half. Then we have residuals from the second half. Okay. We divide the residuals of the first half by the residuals from the second half. This is how we have the value of f. Now to know the p-value, we 1 minus using this function f into our model dot dfe, and similarly here. Okay. Once we have these,
Can also do the critical instead of looking at it, we can also
yes, with the critical value, if it's approximately equal to 2,
is the function
yes, but okay, no, that's another thing. That is when we are doing the confidence interval, when we have the 99. Okay, so you're confusing about this. Here the critical value for us was 2, if you remember. Okay, we say if the Durbin value is approximately equal to 2, so that's the critical value. If the d value is less than 2, there is a positive correlation. If it's greater, there is a negative. Yeah. So based on these calculations, we have p-value this and this is this. Okay. Here the d value, the Durbin value is 1.82, and p-value is this. What this means, we do not reject our hypothesis, okay, because there is absence of autocorrelation. Yes, and this value is less than, when the value of D is less than 2, this means there is no positive autocorrelation, okay. And our assumptions when we are doing a Durbin test, our assumption is there is autocorrelation, there is correlation. But when we did the calculation, this value is less than 2. This means there is no autocorrelation, so we reject the null hypothesis. Is it clear? Okay. Similarly, we did this. Okay. We have one more exercise. Do you want to do, or up to you? Democracy. Who wants to do the exercise? If anyone wants to leave, they're free. And we do it very quick, okay? So, I go through it very quick. It's for you. Otherwise, it's your homework. And most probably will be in the exam. Now I motivate you. Okay. So we have sales of beer, okay? The data set is from sales of beer. And it says, the response, the output is liters of beer sold, okay? How many liters of beers has been sold? We have explanatory variables, follow me. We have size of the shop. We have number of tapes from where beer is coming. You can take beer. Yes, yeah. You should be expert in this. Then we have days of week, okay? We have days of week as explanatory variable. Is it a weekday or off day? Is it a weekend or holiday? And the location of the shop. Is it in the city center or it's in the outskirts? And we have this data for 30 different shops. Okay. Two things here to note from here. We have weekdays, so we have two options. We have day of week, so we have two options in the question. Is it a weekday or is it holiday? So, is it a dichotomous case? So we can use categorical variable 1 or 0. Similarly for location, we can use categorical variable in center or outskirt. So we can model, our model becomes like this. Okay, we have the intercept, size of the shop, we have the tapes, day of the week, location. Is it correct? Is it correct? This model. We have the intercept, size, tape, day of week, location. We include all the explanatory variable to know the sale of beer. First was to make a plot like this, okay, and this plot is called YX plot, okay. You can do this, take your data, day of the week and location, okay. So those are now first you have to convert them to categorical variables, okay. For that we use the function categorical, take from your table, day of the week, similarly for the location. So it automatically converts to day of the week and to plot them in this way where we have 4 adjacent plots, okay. On the x-axis we take what this one means and first column, and here to the last. So all the explanatory variables. Sure? Okay, now some comments about this. If you see to the first, which is number of tapes versus beer sold, okay? We don't see any clear pattern here. Similarly here, but looking here, which is size of the shop and liter beer. So there is what? A linear positive relation. Okay? So if you have a big bar, we all go. Okay, we fit the model this way, where we have all these things. But now, two things to keep in mind. The day of week is a dummy variable, and also location is a dummy variable. So we should include that, okay? If you fit the model, we have these things. What you are noticing? Quick. Look to this last row. Yeah? So p-value is greater. So this means what? Okay, this is this is not significant. We remove this. Okay, so the location is not important. If it's a good beer, if it's outside or in the center, we all go. Okay? And the goodness of the model, 0.99. This means we have captured all the variability. And location, we remove it. Okay? Remember, to remove a particular variable, we use a function, remove term, and that variable. So we remove this variable. So we have a new model now. We refit the model. This time we don't have location. Clear? We look again to the estimated values. Now this time much better. So now all the remaining variables are significant. We keep them in our model. Similarly, you can have observations, conclusions like this. So, holding the size of the shop fixed, the day of the week fixed, and if we include one extra tab, okay, if we include one extra tab and the rest of the explanatory variables are fixed, about 20.65 more liters of beer will be sold. Okay, clear? Similarly, for the size of the shop, if the size of the shop is increased by 1 unit, we sell more liters of beers by this amount. Okay, and also same conclusions you can make about holidays and weekend. Okay. Intercept, same story. Is intercept here meaningful for us or no? No. Then there is a different case which says to test a joint hypothesis. A joint hypothesis means where we combine two different hypotheses. So for example, we say the day of the week is equal to 0. Okay? Similar, so this means 0 days. Number of tapes is equal to 0. We don't have any tape, for example. It does not, these two variables have no effect on the dependent variable, on the output, on the consumption of beer sold in liters. Okay? So if this is true, we have this case. So now we have two restrictions of our model. So Q is equal to 2. To make the joint hypothesis, we make the C matrix. Okay. So what we have, the intercept. Okay. Then we have the number of tapes. Then we have day of the week. Then we have size of the. Okay. And we don't have the intercept. We don't have the intercept, and this is for the size and for the function in MATLAB is to. This is for the beer, for the tabs. So first row, second column, second row, third column for the holidays. We fit this model using this function. Our fitted model plus the value of C. Okay, and it turns out that F value is this and P value is this. So our model is highly significant, and this means we reject null hypothesis, which in turn means that number of tapes and week or holiday these days have effect on our model. Then part 4 of the exercise was to perform a forward selection. Okay. So if we do the forward selection, the function is stepwise. Which one is this? Beer. Okay. Similarly, you look, for example, here we remove the location. Okay. We remove the location. Then we did this step. For stepwise, the function is stepwise LM. We take our data and liter of beers. Liter of beers is what? The output, no? Okay, so we get those values, but just to do it quick here. So if you do this in the forward stepwise, all the variables are important for us. They are all significant. Their p-value is very, 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 very less. So this means all these are dominant in our model. For the stepwise, our model is like this. And this was the same application we obtained manually. So before we did manually, okay, where we looked and we saw the location was not important. We excluded that variable. That is what we done manually, and we then refitted the model. But here with the stepwise, you just write once this function and it do all the steps. And our final stepwise model has selected this model where we clearly see location is absent. Okay, so it coincides with our manual procedure. Similar conclusions you can make for R square and those things. And then you can do also for the residuals, okay? Predictions. You can also make prediction on the same data. And the question says, if the size of the shop is 2000 meters square and the number of tapes are 5. So make prediction for it with 99% of confidence interval. What's the question? The question is, we need to make prediction. We need to make prediction. The new values are, the size of the shop is 2000 meters square and if the number of taps are 5, if we have this condition, okay, so what would be the consumption of beer? And we want to know this with 99% of confidence interval, okay. So 99% confidence interval means 1 minus alpha, we have 0.99. Okay, MATLAB, same story, we have to organize it. Any row, let's say row number 4, where is the size of the shop, and then the other value, okay. So, which is 2000, which is 5, you're predicting what? Liters of beer, okay, with a confidence interval. So we predict, put our model, the new value, which is x naught, okay, alpha is the confidence interval. So 1 minus 0.99 here in MATLAB we say the other way around, 0.01. Then we make predictions on what? We want to do prediction based on our observations, okay, and then we print the values. So it turns out that for point prediction we will sell this much of liters of beer, okay, with 99% of precision or confidence. And if you want to look for the interval, which is from this to this much liters, okay, we are good. Thank you, and see you tomorrow in the lab.